So my name is Johan. I'm the head of the Department of Mechanical Engineering, as I said before, and also leader of research track 3, simulation-driven design. I will start with introducing what I mean with simulation-driven design, and then on an overarching level, talk about what has been done in the profile, and ending with some outcomes of that. But leave the details to the researchers that will present during the day. So I will not go into details, just an overarching picture of what we mean with simulation-driven design and what has been done within this project. Looking at design, we start there. I say here that it's a process about generating products and services that satisfy need in the best way within available means. Issue is that needs and available means are all often ill-defined and conflicting to start this project or this process. And in nature, this is sort of an iterative process where we move back and forth between the problem space and solution space. So framing the problem, solving the problem, and we go back and forth, iterative manner. And we don't really have a right or wrong, it's just better or worse, essentially. Challenge then can be visualized as this. I think you've probably seen this many times before. Product development paradox referred to, where so in starting the project we have rather low knowledge about the new product or service or whatever the new challenge we are facing. Although we have all the freedom to design whatever we want. As we move on, we start to lock in design stages or gates, what has been decided upon, and we lose freedom. This being a challenge with the iterative nature of product development is that we sort of need knowledge to make the correct or the best decisions, and we need to do it early on as sort of we lock the design freedom during the as the project continues. So we need to find ways of sort of changing the derivative of knowledge acquisition in development projects. This sort of seems neat, just showing it like that, but we deal with very complex problems. And engineers deal with complex problems. We need to be effective in how in tools and methods how to approach this. Acquiring knowledge can be done simplified. We can view it as two different parts. Either we collect, building on the knowledge, data information knowledge pyramid, we either collect data or we generate data as sort of the building blocks of knowledge. So either we have through sort of a data-driven paradigm, we have maybe IoT sensors and we collect data from the field and so on, and we move that into information. Or we generate data through building mathematical descriptions of systems and we simulate and so on, generate data and information. This can be viewed as sort of a black box view of things that where we not necessarily need to know much a priori of the system that we're studying. This is more of a white box view of the system where we actually need to know something about the physics of it, its behavior and so on to be able to build mathematical models. Still, it's a push-pull system where we actually need to know what we want to acquire. We need to know what type of data to gather and so on, which is a huge problem. Both of these views use mathematical modeling. Only in this case, we need to know something about the system. In this case, we don't necessarily need to know something about the system. So based on mathematical models, we do experiments. And if there are mathematical models, we use to refer to that as simulation. And simulation-driven design, if we, those of you who have been around for a while have heard so many different descriptions of this. It might be data-driven, it might be simulation-driven, it might be model-driven, it might be simulation-based, it might be data-informed design, or whatever it is. There are so many descriptions of this. Looking at the dictionary, the difference, I would say, if we refer to based and driven, for example, is that based indicates that something is developed by the prefix, the adjective in this case. Or if it's driven, it tells me that it caused or influenced or makes something happen, which is a huge difference. And if it's informed, it sort of indicates that it's based on something more than the data itself, for example. So driven is an active suffix in this case, which is usually important when we define what simulation-driven design is. And it obviously can be defined in many different ways. I have chosen a definition like this. Simulation-driven designs refer to the design process where digital models and simulations are the main means to guide the definition, exploration, search of the design space. So it's an active thing where we actually want models and simulations to guide us, to give us suggestions and so on. It's active instead of passive. That's sort of an overview of what I mean with simulation-driven design. If we then move on then to what we have done within this particular project, focus on the STD research in MD3S Plus has been to overcome obstacles due to limited resources and time. That is looking at modeling strategies, how to model this particular problem, exploration strategies, how to explore the science spaces, for example. Design automation, how to be more effective in generating new concepts and so on. That's one thing. The other thing is to augment decision making by efficient retrieval and interpretation of model generated information. It's very easy to be overwhelmed with data, and there are a lot of data available, and it can generate a lot of sort of an avalanche of data. So how to actually interpret them and make efficient decisions. Then we come to data analysis and visualization as also important aspects of the research in this project. Main responsibility within the project for this research track has been the infrastructure and methodology for the decision arena that Tobias talked about in his introduction. So what is a decision arena? The decision arena is a model-driven environment for collaborative decision-making, a decision arena. So essentially, it's a physical location, which should be a common arena for visualization, communication and decision-making across disciplinary boundaries. Also usually important. And what is sort of used as decision support is digital models, the information generated by those models, data and product data collected in the team. So it's both simulation-driven and data-driven. We'll get back to the decision arena in a later presentation during the day. So based on those objectives, I think we have a similar approach as the previous two research tracks. We have a set of defined research questions. We'll get back to those, which we have sort of then tried to clarify, and based on that, make case studies. All sort of recircling into our decision arena to support the development of that, to support new ways of working in that type of environment. But we have dealt with an exploration of the science basis, how to interpret that data, which might be different visualization strategies and data analysis strategies. We have talked about trust in these decision scenarios, about model maturity, which I think Christian will talk about today. We have touched upon data-driven design, even if the emphasis in this particular track has been simulations. We have also used data-driven designs. We have digged into more advanced, detailed simulations on a core level and dealt with design automation. Through these use cases, we have worked on all the research questions that was sort of stated in the initial application. But I won't go into details. I think we will sort of recircle to all of this more or less during the day in different presentations. Outcomes. Looking at the last 3 years, which is the Profile Plus. From this research track, we have 3 licentiates, 2 doctorals, 8 journals, and 9 conference papers. We have had several best paper awards. We have reviewer favorites among these and so on. So it's been received well. From this, we also have spin-off projects on different topics, not the least sheet metal forming, which is now, we have a group at BTH working on that with senior lecturers, postdocs, PhD students, which one non-existing before the profile. So that's a huge success. We have influenced our educational offers with new courses, design automation, simulation-driven design, and so on, which is active as of now. Also have an influence on where we're going from here. BTH is sort of transitioning from the current system into 3+2 Bologna system, where we have an influence on the proposed masters in mechanical engineering from this track. Some of the findings have been productified, implementing some of the simulation procedures in commercial software and so on, which is also really, really nice outcome of the research. Not the least, we have the physical space of the decision arena itself, which is an outcome. But as I said, we'll get back to that in a later presentation. So where are we heading from now? This is all built up to what we refer to today as the digital twin and the digital thread. This is where we're heading. These type of modeling strategies form basis in the digital twin. Also, in a wider perspective with the digital thread, where we include sort of the whole life cycle of the product from concept to retirement, essentially, and collecting data streams for that, and influencing the development of the next generation of the product and so on. And I think Marco will reiterate to the digital twin during the days. That was a short introduction to the topic and what has been done, and we'll let the researchers themselves go into the details later during the day.